Welcome back to the video lecture series for Introduction to the Art of Programming Using Scala. In this video, we're going to continue the coding that we did that we started in the last video. We continue looking at multi-threading and the Java util concurrent package, and we were writing a program that was supposed to demonstrate the use of a cyclic barrier. So this program is intended to demonstrate a simple crystal growth simulation. It has a single buffered image that we display, a panel, a frame to hold that panel. The panel just draws the image. And down inside the main, we open up the frame. We create an executor service. And in fact, I should make sure down here, after the for loop, that we shut down the executor service. I make an array of points that holds as many as we're going to have threads, and then I made a cyclic barrier which also is basically going to cycle around on that number of threads. Remember, the difference between a cyclic barrier and a countdown latch is the countdown latch counts down exactly once, whereas the cyclic barrier can be used over and over again, which is why we declare it out here. And then I go through for the different threads, and each thread has the following code inside of it. There's a while loop that makes it so this is going to keep going until we have placed 10,000 points, and then each time through it starts with a flag at true, and it makes a point that has a random x value and y is 0, so it's some point along the top of the image. We haven't filled in the code that is supposed to move this xy around but we'll do that in just a second. After it has found a place to put this, in other words, it gets to a location where the next move would have taken it into another crystal, then it stores that and it calls await. After this call to await, so basically all of the different threads will wait at this point until all the others are done. When the last one gets done, it comes into here, and if you happen to be the first thread, then you're going to plot all of those points onto the image and call await again. So then all of the threads will wait right here until the first one is done plotting. It does the plotting and it increments the count, and then they will all cycle back up to the beginning of the while loop. They will check that count, and we're continue going through this. Note that in this case, I'm not synchronizing on anything. Even though count is a variable that's being shared by multiple threads, it's being written here, it's being read here, and this array points is being shared by multiple threads. Now the writing, they all write to separate locations in it, but they are we're going to be reading out from them. One thread is going to be reading all the different points here. And also inside of this, we're going to be checking an image. So we have several pieces of data here that are shared between multiple threads, but I don't have to worry about the synchronization. And I'm not using synchronize anywhere simply because the way that the access is done in between, so in this section, for example, this actually includes the while loop. This is read-only. None of the threads are writing on this check. The image is going to be read-only here, and the points, while each one is going to write, they're only going to write to their index. This and that is separated from this section here, which is going to change count, and it's going to change the image, and it's going to read out of these points. But all of this is being done in a single thread, and it is separated from these other operations by the awaits. So we don't have to worry about race conditions, not because we've synchronized them away, but because we've monitored the flow control so that the operations basically on one side of this barrier, you're only doing one type of operation, or you don't have conflicts, and on the other side of the barrier you're doing another type of operation, and so the two don't have a chance to conflict with one another. Well, when I write code, I often tell my students this, I want to start with the easy stuff, and it turns out moving the crystals is going to be a little bit more complex than plotting them out. So I'm going to do plotting them out first. This is fairly simple. We can run through a px and py in PNTS. I'm using a for loop because this is a tuple, and it's nice to be able to use the pattern to pull things out that way. And then do img.set RGB of px py color.white.get RGB. So I'm going to set the color on the pixel at that location to be white. Okay, so now let's come back up here and decide how we have to move. As I said, this was the easier option. So the first thing I want to do here is I need to basically make a new version of x and y and make it so that they are randomly offset from the last one. So I'm going to say the new x is the old x plus util.random.nextInt of 3 minus 1. And I'm going to do the same thing for y. Now, you might wonder what the heck's going on here. So nextInt of 3 returns a value of either 0, 1, or 2. Okay. When I subtract 1 from that, so I have that value minus 1, that means that I'm either going to get -1, 0, or 1. So this gives me back the x location that we're currently at, either -1, not moved at all, or +1. We're going to do the same thing for y, which means that whatever square we're at, this has the ability to move to any of the 9 squares, including the one that we're on and the 8 around it. So in other words, this is doing a random move allowing diagonals. Now, what are some possibilities here? Well, first I need to check what if this new position is out of bounds. Okay, we don't want to be trying to call a get RGB out of bounds. So if nx is less than 0, or actually, let's go the other way, because in that case, I'm actually going to do absolutely nothing. So if nx is greater than or equal to 0, and nx is less than img.getWidth, and ny is greater than or equal to 0, and ny is less than img.getHeight, well, that means that the point that we've moved to is inbounds. And now there's one of two possibilities. Either we're going to move there because it's blank, so I want to check the image, and I want to say if img.get RGB at nx, ny, and this is why I had to check the bounds on nx and ny first, is because otherwise this would be reading from outside of the bounds. If that is equal to color.black.getRGB, then I want to do one thing, else we'll do something else. What if it happens to be black? Well, if it happens to be black, then I set x and y equal to this new location, and we're going to repeat and move from there and repeat and repeat. If it's not equal to black, though, that means that we're done, and the x actually needs to stay where it is because this new one was on top of something, we ran into it, and all I need to do is set flag equal to false. That will terminate this while loop and jump down to here, use the x and y location that was right next to the thing that we stuck to, and store that into points, and then await. Okay, so we've written the code. Now it's time to debug it and see how well it works. Nothing. Now, in some ways this might actually not be too surprising. I didn't put in a repaint. Hey, look at that. There's actually crystal growth down there. Let's put in a repaint. So after we are done drawing this. We'll call panel.repaint. And now let's try running this again. And hopefully you can see down at the bottom here, we have some crystal growth. Now what you can't see is the load bar on my machine, which is pretty much pegged with all 4 cores going just about full time, which it should be because this is happening across 6 threads. If this were only happening in 1 thread, actually let's do that. See if I can bring up a system monitor and let you see this. Okay, so there's my CPU usage right now, using the 6 threads. We're keeping the system fairly busy, and it looks like it finished growing, but for some reason this did not all terminate. That's a bug that we need to look at. Okay, let's come back over here. Before we look at that, we can also do something like set num threads to 1 and rerun this. I have some other processes which are of course keeping things a little bit conflicted here, but you can see that my load isn't quite the same. I have a browser which is up and doing quite a bit of work, but we're not fully utilizing the system. This would be even better if you happen to have a machine that has 8 cores or 16 cores or something like that. It would be good to push this further and demonstrate how you can keep the entire machine busy by keeping all the threads in use. Now, the only other thing that bothers me here is the fact that, I'll take this back up, actually 4 is a good number, is the fact that this did not terminate. So this goes until the num threads. An idea occurs to me. One thing is I'm technically not waiting for all the threads to finish before I call es.shutdown. That bothers me a little bit. So we could get all the futures, and I just want to print something so I can see. Okay, that will make it wait for everything. Oh, okay, never mind. It just hit me. As long as the window's up, until I close the window, the application is going to be running. Obviously not thinking clearly here. But it will be nice here to make sure this prints out done, so when the crystals stop growing after it's placed all 10,000 points, it should call get on each of the threads, and technically it's called get on the threads right now, it's just they haven't completed yet. So note that when you call the shutdown on this, there were 2 versions of shutdown. This one doesn't force it. I think there's a shutdown now, which will kill the threads. It's a risky thing to do because it can leave your program in a bad state. Here we go. We have some printouts of done, 1 for each thread, and it happened right when this finished growing. So our ES, the executor service, has shut down, but we still have a window up, so the application is still running. So that's it for this program. This shows you how you can use an executor or how you can use both an executor service with the fixed thread pool, and how a cyclic barrier can be used to synchronize threads doing things, and also how carefully thinking about where you're doing reading and writing from memory can allow you to have things that are thread safe even though you aren't doing formal synchronization. You aren't using the synchronized call. Instead, you're using things like cyclic barriers to keep operations that would conflict with each other separate inside of your program. So that's it for this video. In the next video, we'll come in and we will talk briefly about the Java util concurrent.locks package.